let's continue with our graph implementation. So I made some changes to the code during the break. Basically, I added a little helpers construction because the node, let's go to what are we using? We have our node, right? It's kind of useless, but because we don't have a string. If you had some more properties, it'd be useful, right? We have edge. And so I made a set of node IDs because it's simpler for me to just keep track of checking node IDs, assuming, there's only one A, right? So I don't get any duplicates. So here, when we're adding edge, we check whether such a ID exists, basically, right? And then add node, we added this extra, again, memory is relatively cheap. This node ID is not going to take some extra storage. Again, just a little helper method. Obviously, you could live without it, right, if memory was at premium. Now, what else? What else do we need? So we have add edges. So what we have? We have basic. We can add. We can print. We can print the graph. And I want to show you that I also added, a little extra edge, right? Just to show you that, of course, you can have duplicates. Of course, you have multiple, neighbors, right? And a node or vertex could have multiple neighbors, of course. Right, so let's test it now on a CSV file, right? We did all this work. I want to get some graph. Let's see, maybe let's do cities, Latvian cities and CSV, right? Let's do this. So, right, rainbow install, I used also, all right, this is good. Right, so I will assume so Riga, Tukums, right, and we'll date like 67 kilometers, right? Riga, Jelgava, 41, okay, why not? Riga, Ogre, 37, looks pretty decent. Salaspils, 18, I guess so, right? And I guess enough for that. So let's do Tukums, Jelgava. Yeah, Tukums, Jelgava has connection. Let's assume yes. That sounds also reasonable, right? Tukums, Ogre is fake, and I'm not going to use it, right? So we'll assume Tukums, Ogre, there's no direct driving, of course, even though technically there is, right? So where else we want to do? We have only 5 cities. Let's do also Riga. I guess that's enough. Only so you have how many? 5 nodes, right? 5 nodes. And let's see. Ogre, Salaspils, right? Ogre, Salaspils, 23, I guess so. And Jelgava, Salaspils, I suppose, right? Right, Jelgava, Salaspils, sure, why not? Right. So this is directed graph, assuming it's only one way. Again, of course, assuming is this only one-way connection, right? Again, but let's go with it. Let's roll with it for now. So it took Jelgava, Ogre, Salaspils, Jelgava, Salaspils, and Tukums, Ogre, Jelgava, and Salaspils doesn't go anywhere, right? Salaspils, Riga, I guess, yeah. I guess you let people go from Salaspils to Riga, right? So yeah, so looks okay, right? Now we have our little edges, right? So these are going to be, of course, directed edges, right? So let's see if this works, right? The big test. So graphs, Latvian cities, will it work? It worked. Yeah. So Riga has lots of neighbors. So Tukums has neighbor, but no. Okay, this is good. So Salaspils has a Riga. Riga has neighbor Tukums, neighbor Jelgava, neighbor Ogre, neighbor Salaspils. That's good. Salaspils has neighbor Riga, but what's happening here? So Jelgava has neighbor Salaspils, Ogre has neighbor Salaspils, Tukums has neighbor Jelgava. But what's up with this? This looks kind of weird, right? You have 10 nodes, yeah? 1, 2, 3, 4, no, wait, that's wrong. So that is wrong. I know what's happening, right? Probably the white space, yeah. You know what the problem is? Classical problem. White space problem, right? Something you will encounter, right? I did not strip the white space here, right? I could do it basically by fixing. I guess I'll do this, right? I'll fix it for now, by being strict with my code, right? That's a kind of obvious error, right? And these numbers, well, I think numbers will be, right? But it would be actually something to be nice. Yeah, we have 5 cities. Now everything is good. Salaspils, Ogre, Jelgava, Tukums, and Riga has 4 all neighbors to everybody, right? You can go from Riga. So the question, of course, is, can you go from Jelgava to anywhere? Well, can you reach all? So how do you go from Tukums to Riga, right? Not assuming this is directed graph, right? Well, how do you do it? Well, you can't go to Riga directly. You only have Jelgava. So, on Jelgava only has connection to Salaspils, right? So, to go from Tukums to Riga, you go through Jelgavas and Salaspils. Only then do you get to Riga, right? Yeah, kind of. Again, not very efficient, but that's what the graph would say if it's directed graph, right? If this is undirected graph, of course, then we have to create these counter weights. Okay, but now of course, now this works. That's good. Let's add this. Riga Latvian cities. Latvian cities, right? That's good. We have our nice extension, right? These are should be colored. Why isn't it colored now? It should be colored. I don't see it. But okay. Um, Now we need to add traversal, right? We want to traverse, meaning we want to find whether there is a connection. Let's add a traversal, and typically we do it with a DFS, right? And this is an algorithm, right? DFS should be one of your, should be in your brain, right? So we start somewhere, right? We do it recursively because that's, well, for now it's easiest, right? We visit something as visited, right? We visit the node, right? And for each neighbor, we check, right? But of course, we start that first traversal, so it's going to be recursively, right? We'll go whichever first we find, right? We keep doing it, right? And idea would be, of course, to find, can we find the connected, right? So we will provide source destination, return Boolean, right? Let's do this, right? So we have a graph, the constructor. Let's add a depth first search that checks whether one can reach destination from source. All right, Boolean DFS. We will need a helper, of course, right? And we will need to add it where, right? Source. We're gonna pass this another set of visited, right? And let's see if this. Can we do it here? Yeah, we need this recursive helper, right? If source equals destination, right? That means we reach it, right? That's good, right? Right. Otherwise, mark source visited and check all neighbors, right? This is not finished. This is not finished at all, right? Auto neighbor, right? If visited. So this is recursive. We do a recursive call. So we do a recursive call. All right. And we pass this visited data structure, right? As from unordered set. So we pass this unordered set, right? Okay. It would be nice to, let's start with this one. Let's check. Let's do this. If, let's assume we want to check. Let's add a check. Let's add a check equals 2, right? Right, 2. Right. If there are 4 arguments, well, yeah, from that graph, yeah. If, yeah, we create the argument, right? Can reach, right? So we'll check Tukums to Riga, right? Let's see. It looks okay. We didn't check for 3 arguments, right? If there are 3 arguments, right, assume it's just bad, right? So for now, you have to, of course, check other ones. Okay. Do you guys see this, where I'm going with this, right? DFS? Yeah? More or less? Or maybe not so. Right, so DFS, recursive, or base case. Base case. So, questions, there's some problem here. The problem is this, right? I think you should probably do this, right? Return false, right? I think so, right? Yep. Now I think we are good, right? If you reach here, means we cannot reach destination, right? It means we are basically, I wouldn't say screwed, but basically we are in bad shape, right? We can't go home, basically, right? So, base case, we mark visited, and keep going, right? Keep going through all the neighbors, right? So potential, of course, this could take a while, right? Well, the good news, of course, is that it should not take forever, right? Because, well, you have multiple routes, of course, right? But you're visited. One thing is this actually going? One thing I'm wondering is this going to work, right? Because DFS helper, right? Yeah, here, right? We check. Is this going to actually remove this? That's one thing. Is this a problem here? I think, right? Is this actually recursive call gonna work or not? Let's see. No, it should work. I guess it should work, right? Because we have visited. Okay, yeah, all right. So finding whether we have connection should be pretty quick, right? Because I'm trying to imagine if it could be a reverse, right? Because just imagine, I'm thinking, is this going to work? There actually might be a subtle bug here. Because we mark something like B as visited, and there's no outgoing connections, okay? And then we check C, right? But of course, no, yeah, no, it will work, because if see there's no outgoing connections, of course, that's, if there's no help, there's nothing good, right? Yeah, okay, everything will be fine. If you can go from C to B, right? Well, we only checked B, so this is going to be fine. Yeah, no bugs. I don't think so. Well, I can't prove it yet, but let's see if this works. So, let's compile it. Oh my god, so there's one little, I forgot to close something, right? Return, yeah, here's a little curly brace. Let's do that. That looks good. Let's do Tukums. All right. Now let's do Latvian cities, and let's do what? Tukums Riga. Tukums Riga. Can reach Riga from Tukums. Okay. Let's be evil. Let's be evil. And we are going to do what? I guess we can remove Tukums Jelgava, right? Tukums can, well, again, every other city has connection. So if I remove this line, right? Right, Control S, right, let's do it one more time. Cannot reach Riga from Tukums. So yes, looks like it's working pretty well. Now, of course, what we would like to do is, remember, this only finds any connection, right? It's not going to find the best optimal route, right? Because depth first search, the first thing it hits, it will give you a solution. But again, it's good enough. Again, the goal is, I don't think we'll get here today, maybe on Thursday, to use it for max flow. Remember, we're going to need to find these augmenting paths, right, from somewhere. When we have this possible or residual graph, we're going to be building a residual graph and keep looking for these paths using depth first, or maybe something else, right? But we'll be able to keep doing this until we cannot do any more, right? Keep finding new paths. Okay, so let's go back to Tukums. Control Z. Let's go. All right. Now we would like to, right? Let me add this. This works good. DFS basic search, right? How would we? Yes. Let's add an option. I guess we will. How could we? We will need to pass actually the pass, right? Let's add a pass, right? Return DFS helper, and we'll need also a pass, right? Not Boolean, right? Yeah. Let's return a pass, or empty vector if that's not easy. Okay, yeah, let's do that. So let's revise this, right? So this is going to be what? A vector of something, right? Vector, do we have vector here? Yeah, we do have vector of something. Right. My AI is not helping me here, come on. String of, right? And I guess it would be strings, right? Was it like this, right? I keep wrong. No. Yeah, I guess so. Now, what's happening here? This obviously now returns Boolean, right? So, we are going to do what? Vector string, right? Unordered set entered set pass, right? And we pass as well, right? And let's see, this is kind of tricky, right? We're gonna pass this here as well, right? And we want to this the boolean. I guess we'll just basically pass return. We call it, right? You know, there is pass. You know, I guess is pass bool is pass, right? But it's not really needed, of course, right? Just show you that it works, right? And of course we return what? Pass, right? We need pass, put pass here, return pass, right? Return pass, right? Right. Vector string, right? And otherwise we just get empty vector, right? Is there pass, right? You know, now, so the only thing we need to fix is this part here, right? So let's make it, since I'm lazy, I'll make it like nicer, hopefully a little bit, right? Lots of stuff here. I would like to adjust this. Come on, right? Yeah, and of course we want to add one more, right? On order set string pass. Okay, of course, using a reference, right? Because we don't want to, you know, no pointer stuff. So, okay. So what do we need to do? So if source destination, we need to, of course, probably not do nothing. So here, right? Pass insert source, right? That's it, right? So this should find some pass or find nothing, right? Yeah. So, okay. Let's see if this works. On print pass, right? We want also DFS, right? And since we are doing this pass, right? We probably want to also, you know, print it, right? Right. So let's do that. What's happening here? Ah, yeah. What's the problem here? Right. If, right. So we'll do something different, right? So, right, pass, right, print pass. Okay, something like this. We will probably might make a function make a function for this, right? If the pass size over 0, there's pass. Otherwise, pass does not exist. Okay, looks pretty good to me actually right now. Maybe there might be a subtle bug, of course, as usual. Let's compile this, all of this wonderful stuff. Yes, all right. Expects 4 arguments, 3 provide DFS helper. So what happened here? Aha, this part here, right? We need to put pass here, right? Of course, right? We have a recursive call. You need to put pass, right? Again, so that's why, of course, C++, unlike Python, you know, if you have a correct, good, strong type system, right? Well, this is kind of loose in a way, right? You'll be able to catch all these type of errors because you provide a good function or method signature. You'll be able to fix these errors very quickly. Now this looks better, but let's see if this works now. It compiled. That's a good start. Let's take a look. All right, passing. So Jelgava Salaspils Tukums. Well, Tukums Riga. Ah, it's reversed, right? Jelgava Salaspils Tukums, right? And we want, it keeps adding these. Tukums Riga. Yeah. Tukums, how the heck does it work? Tukums Jelgava Salaspils Tukums. Ah, Tukums Salaspils. No, something's quite not right. It looks okay. Let's check it out. Tukums Jelgava, right? We are finding from Tukums to Riga, right? So Tukums keeps going for neighbors, Jelgava. Jelgava should add Salaspils, and Salaspils should find Tuk Riga, right? For some reason the path exists, but doesn't print it correctly, right? Let's double check how can we improve it, right? We keep base case, right? And we add this here, right? Maybe let's add this. Pass start with source, right? We always do it here immediately, right? So let's double check how we do it. We check source, right? Tukums. We say it's, why is it Tukums last? I'm trying to see how did we print this, right? I'm trying to see how did we do this. Auto. node pass, push them back. Yelga was first apparently, but no, it's still not. Tukum should be first. I don't know why Tukum is last. And why is not Riga not present, right? We're trying to get to Riga. Right. This is our main thing. Source destination. So maybe we should add here. I'll see if this is pass insert. I don't know. Let's double check now. What's going to happen? Riga, Yelgos. Okay. So something is a little bit off, right? Pass exists. We go, for some reason it thinks that the source, yeah. Why is Riga first to come? Let's see. We have adjacency list. No, let's see. Why didn't it print it? Pass, right? You get a pass. It's correct because we're not going through Ogre, right? Obviously. But why is it actually? If we can fix it, we can finish early today. We're doing apparently something with recursive functions here. Or the pass insert is insert. Oh, it's an ordered set. Oh, all right. That's why. Okay. Sorry, guys. Yeah, that happens if you're not paying attention. Sets unordered. Keyword unordered, right? It does not make guarantees of a specific order. We just put stuff in. It's still very useful data structure, right? But we don't have the order. So what I could do is ordered set maybe. Yeah, it will work. It's in fact, if you check our documentation, we'll talk about STL on Thursday, right? Set. I don't have set, of course. I'm going to import it, right? I'll do set. Let's include set. Yeah, exactly. Thank you, AI. It's very quick. Right. So this is ordered set in C++. Very important point. Meaning all login operations, right? But ordered, right? Pretty nice. Let's do that one. Include set. We could use also vector, of course, right? Vector will be here fine as well, right? Because it's sequential, but let's do order set. And where are we? Now it should be better. So pass is, of course, set, right? Yep. Okay. Our signatures are good, I hope. So DFS, ordered set. And our signature here for DFS helper is also set. Okay. Let's see how it goes. That happens if you use the wrong data structure. Compiles, alright. And Jelgava Riga Salaspils Tukums. What the heck happened now? Riga is Jelgava Riga Salaspils Tukums. Again, path exists. I guess we'll just have to go vector because again, maybe we have the wrong order, right? And maybe we're doing it, pushing it in the wrong order, right? So path is present, but somehow Jelgava Riga doesn't make sense, right? Jelgava was the first, but then the Rigas and Salaspils and Tukums. It's a question how we visit, right? And how we write, how we push onto this path, right? Path insert, right? Let's do this. Let's do a vector, and that will make our sense because we want a sequence, right? Of course, let's go to the vector, right? So let's go this. So, or DFS, we'll use vector. Let's use vector. Let's use vector for, right? So, no vector. I said vector. String path. So I need to, of course, say vector string, right? So I need, of course, DFS helper says, okay, I don't know anything about this, right? So you want to say vector, right? Right? Do we have insert? We don't. We have something else, right? We have something called a pushback, right? This also will be pushback, I hope. Right, pushback. Let's see. Alright, does this change? Not auto still stays the same for pass, auto node pass, right? Right, string node, right? Alright. Hopefully this works now. Rainy. Tukums, Jelgava, Salaspils, Riga. Yes, all right. Now we're cooking. So everything is good. And could you add a distance? Sure, right? Well, now of course we have these sources, right? We could have a helper function. Basically, let's take a method. Given a pass, recreate costs, right? Why not? Let's make a helper function. Let's do that. We can of course save it, but we don't need it. We have a pass. We can get a easy to get the cost, right? Let's make a function. Let's make a function that takes in pass and returns cost. Right? Double pass cost, double cost. For int pass size -1, auto neighbor adjacent listed. If neighbor list pass I plus 1 cost. Okay, let's see if this is correct. We have pass, we check, right? Cost plus equal. Otherwise, right? Cost plus equals second, right? If we check, right? Cost plus equal neighbor second, right? If neighbor first equals, right? Pass equals 1, right? If we find it, right? Then the cost is from the second, right? Else, right? This means here, right? Well, means here we will need a flag. Basically, this works, right? So this function, I will not fix it right now. This function will return true cost as long as pass is valid, right? Otherwise, it will only return cost of the valid part, right? It will keep going until it reaches, a dead end, right? And then it'll give you the cost. Makes sense, right? Okay, let's test it, right? We have our pass. Do we have our pass here, right? Pass exists, right? And print cost, pass cost, right? We can do it. Let's do it, right? Now, let's see. Pass cost. It should be home something, right? Let's double check, compile. Oh, pass size, okay. This looks like a type error. Pass size is what, size T, right? Yes, size T. I is okay, so we just fix it size T. Right? Let's compile it again. Yeah, okay. Pass cost 93. Okay, let's do our sanity check. So, Tukums Jelgava 45, Jelgava Salaspils at 75 together, and Salaspils Riga 93, right? Yeah, plus 18, 93. So it works. We fixed it. Okay, good. So, super. Right. So on Thursday we will be doing trying to implement maximum flow in C++. Hopefully, right? Hopefully. All right. We'll see how it works. Because we have our DFS, and that's our basic building block. We're almost done basically with maximum flow. We just need to build a residual graph, and we can keep finding these paths, and eventually we'll have a full, when we have no more paths, we'll have a full maximum flow built. Okay, thank you everyone, and we'll stop a little bit early today, and